Okay, let's continue. This is 11.8. We were deriving the formulas for compound interest. A here is the accumulated balance. P here is the original principal. So all those formulas we have seen earlier in previous videos can be represented by one formula. Is P times, inside the parentheses we have 1 plus R over N. On the shoulder of the parentheses we have N times T. N here is the number of compounding period for 1 year, every year. So if the interest is compounded annually, N equals 1, once a year. If the interest is compounded semi-annually, N equals 2, twice a year. If the interest is compounded quarterly, N equals 4, 4 times a year. If interest is compounded monthly, N equals 12, 12 times a year. If the interest is compounded daily, N equals 365, right? And the exponent on the shoulder of the compounding factor, that's the total number of compounding periods over the years. T is time in year. N is the number of compounding period for 1 year. So N times T is the total number of compounding period for the time when your money is in the account. That's one formula. So what if the interest is compounded continuously? Then this formula doesn't work anymore. It's not like once every day or once every hour or once every minute. It's continuously compounded. So then the formula is different. You would have to let n approaches infinity. The limit of this function is this function, a equals p times e to the power of r times t. E here is the natural number, Euler number. Is an irrational number, remember, that's the base of a natural logarithm. Is about equal to 2.718. R here is annual interest rate, T here is time in years. So you would know this why this function is the limit of this function as n approaches infinity when you take a calculus 2. So we don't talk more here. So we need two formulas, okay? For the compound interest, let's look at example 1. Savings accounts. Find the accumulated balance A in a savings account. If you have $5,000 is invested at a 6% annual interest rate for 20 years. If the interest is compounded A annually, B, so we have A, B, C here, A, B, C, D, quarterly, C, daily, we use 360 for the year, D, continuously. So let's see how do we handle this problem. Part A, annually, we are looking for accumulated balance A, right? So find the formula. A equals P times 1 plus R to the power of T. What's P, the original principal? 5,000. What's annual interest rate here? 6%. Converted to decimal, expresses in decimal 0.06. T, time in years for 20 years. I will give you the chance to compute this expression. We don't take time here. Part B, interest is compounded quarterly. And what's the formula? 4 times a year, right? So the compounding factor would be 1 plus quarterly interest rate, which is R equals R over 4. And the exponent on the shoulder of the compounding factor would be 4 times T. Value for P, 5,000. 1 plus R still annual interest rate 0.06, but divided by 4. exponent is 4 times 20, right? C, part C, daily, A equals P times 1 plus R over 360 to the power of 360 times T. P is 5,000. Compounding factor is 1 plus daily interest rate, 0.06 over 360. Exponent is 360 times 20 years. D. Interest is compounded continuously, a different formula, P times E to the power of R times T. Original principal, 5,000. E to the power of R is 0.06, T is 20. So the exponent on the shoulder of E is 0.06 times 20. In previous videos, I have shown you how do you evaluate those kind of expressions using calculator. So we are not spending time here. I have the final result in my notes, so look at the note for the result. Example 2. Example 2 is a problem about exponential growth. When we talk about the definition of exponential functions, we divided all the exponential functions into two categories, right? If the base is bigger than 1, exponential growth, because the curve is increasing. If the base is between 0 and 1, then the exponential function is decreasing. That gives us an exponential decay model. In example 1, when we consider compound interest, you can see those functions, they are exponential growth because the base, the compounding factor is the base of the exponential function, right? The base all bigger than 1 because it's 1 plus a rate bigger than 1. So also E here is about 2.718 is also bigger than 1. Compound interest problem is one case for exponential growth. Here we have another exponential growth problem. Let's look at the problem. Cancer cell growth. Certain cancer cells grow according to the formula y equals y sub 0 e to the power of 0.5 t. Okay, so let me copy down the formula or the function y equals y sub 0 times e to the power of 0.5 t. The base is also bigger than 1. The base actually is root e. You can use your calculator to double check. Root e also bigger than 1. So this is still an exponential growth because the base of the exponential function is bigger than 1. Y sub 0 is the initial number present. Why is that? Because if we let t be 0, this part would be 1, right? And the amount of the number of the cells would be y sub 0. So y sub 0 is the initial number of the cancer cells. T is measured in days. If y sub 0 is 200, means originally there are 200 cells. In how many days will the cells number 200,000? So we are looking for t, right? The goal here is looking for the time. In how many days the cells would increase to 200,000? Suppose after t days, the y would be 200,000. 1, 2, 3. Look at this equation. This equation gives us an exponential equation. So let's solve this exponential equation. Firstly, I would get rid of the 200. I would divide both sides by 200. and I would have e to the power of 0.5t on the right hand side. And what's the number on the left? 1000, right? For convenience, I want to switch the order of the two sides of the equation. I have e to the power of 0.5t equals 1000. This is we are looking at an exponential equation. It's not elementary because it's not very straightforward to write both sides as powers with the same base. So remember, how do we handle that kind of exponential function? We're going to apply ln on both sides. Okay? We're going to apply ln, natural logarithm, on both sides. Why wouldn't we use a common logarithm? Because natural logarithm is better. Because here we have e, right? You would see the benefit right in a moment. So let's continue here. Then we would have ln e 0.5t equals ln 1000. Look at the anti on the left. The anti of the logarithm on the left. It is a power, right? We are able to move the power, the exponent 0.5t in front, and then multiply by ln e. As I said, you see the benefit now using natural logarithm instead of common logarithm, because ln e is 1. ln e is 1. So we have 0.5t on the left equals ln 1000. Divide both sides by 0.5. We have t equals ln 1000 over 0.5. It's actually twice of ln 1000. If you use your calculator, you would see the value. Let me see what I have. How many days? 13.82 days. 13.82 days. So if we round it up, it's 14 days. Just in 2 weeks, the number of cells would increase to 1,000 times of original number. That's exponential growth. Very powerful. Example 3 is a case for exponential decay. The base decay. The base of the exponential function is between 0 and 1. Decay. All right, let's see. Let's read the problem. Half-life of a certain substance in a radioactive fallout is decreasing. The amount of the substance is decreasing, is losing. Find the half-life of the substance using the formula y equals. So let's see the formula here. Y equals y sub 0 e to the power of negative 0.02390. Let me explain. Why do we have an exponential decay here? Why is it decreasing? Let me rewrite this part. E to the power of negative 0.0239 to the power of t. So that actually is 1 over e to the power of 0.0239. The base is between 0 and 1. You can double check by using your calculator. It's a reciprocal. It is the reciprocal of a number bigger than 1. So the number inside the parentheses is between 0 and 1. So the function actually is the second category exponential function. The function is decreasing as t getting bigger and bigger. The amount of the substance is getting smaller and smaller. All right, so this is exponential decay. We are looking for half-life. What is half-life, by the way? Exponential decay is this way, right? We have this curve the beginning of this chapter. Half-life is the time it takes the substance to lose half of its weight. Okay? So in the beginning, you can see the weight is losing very fast. Later, the substance is losing its weight very slowly, very slowly. So where's the half-life would be? Half-life would be here. Okay? Half-life is definitely not half of the lifetime. That is a misunderstanding. It would be shorter than half time. It would be shorter than half of the lifetime. Because in the beginning, because it's not linear. If it's linear, yes, half of the lifetime. It's exponential decay, decreasing. In the beginning of the decay, it is losing weight very fast. In the end of the decay, is losing the weight very, very slow. So the half-life gonna be shorter than half of the lifetime. Am I clear about that? Yeah, so you can repeat the video and really try to make sense of that. So we are looking for half-life, so we are looking for T, such that after that time, the amount of the substance is half of the original amount. You see what I'm saying? After T time, after T years, the amount of the substance is reduced to half of the original amount. So if we divide both sides of the equation by y sub 0, y sub 0 is cancelled out. So we actually do not need, we don't really need the value for y sub 0 at all. So we have half on the left, we have e to the power of negative 0.0239 times t on the right. Again, we are looking at an exponential equation. How do we solve it? We apply the same way. Apply ln on both sides. Okay? And this time on the left, I'm going to do something. ln, I'm going to write half as 2 to the power of negative 1. On the right hand side, we have ln e, negative 0.0239 t. On the left, the logarithm has anti 2 to the power of negative 1. That's a power. By the power rule, we are able to move negative 1 in front. So we have negative ln 2 on the left. The logarithm on the right hand side, the anti is also a power. By the power rule, we are able to move the exponent negative 0.0239 t in front of the logarithm. Okay? By the way, what is ln e? Again, ln e is 1, so we have 1 here. Okay? Also, both sides are negative. If I multiply both sides of the equation by negative 1, I would change both sides to positive. So here we would have ln 2 equals 0.0239 t. Divide both sides by the coefficient of t, 0.0239. We are solving the equation for t, right? We need to isolate the t on one side of the equation. So we divide both sides by 0.0239. Then we would have t equals ln 2 over 0.0239. Yeah, use your calculator. Use your calculator. I have the result that is about equal to 29 years. The radioactive activity goes very slow. Oops. Yeah, even for a very small amount of substance, chemical substance, This is 0.0239. So we get a t about equal to 20.